Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Damia Balkis binti Bakhtiar. My matric number is D202511199484.
Assalamualaikum and good morning. My name is Naima Balkis binti Zuma Maslawati Alai Susu. My matric number is D2025111650. Today, I will present a very important topic in calculus, which is a partial derivative. Before we go deeper in our topic, let me introduce you about our main objective, which is this. First, understand the definition of the partial derivative using the formula. Second, identify and use reference symbol or notation for the partial derivative correctly. Third, solve the basic problem with the partial derivative by holding one variable as a constant. Our first slide, which is the definition of the partial derivative. First, formula is f sub x x y equal to lim h equal to 0 f x plus h y minus f x y over h. Notice that we only added h and s, and we will treat y as the constant number. Same also like second formula, which is f sub y as y equal to lim h equal to 0 f x y plus h minus f x y over h. And same also, notice that we only added h and y, and we will treat x as a constant number. To represent this operation, we will use the special symbol, which is a partial over partial x and partial over partial y. It may look like a quality, but it actually pronounced as a partial. Remember that we cannot differentiate at the same time, and we must differentiate it one by one. If a question asks you to find the partial derivative with respect to x, the symbol might be f sub x xy or f sub x, which is the substrate style. Same also, partial f over partial s and partial sec over partial f. We call it the Leibniz notation. And some examples will also use the partial over partial s f xy and g1f and g sub xf. The exact same style we use when you differentiate the partial derivative with respect to y. So just replace the symbol that have x with the y. Now let's move on to the first example, which is the question asks us find the first order partial derivative f sub x and f sub y for the function f xy equal to 4x cubed minus 5xy squared plus 2y double of 4. To find the f sub x, we will differentiate the first term, which is 4x cubed, and we will get 5x squared. And for the second term, we will differentiate and we will get 5y squared in the bracket of 1. Where we differentiate x, we will get 1, and we treat y as a constant. And same also like the third term, which is 2y to the power of 4, and we will get 0. So the answer for the f sub x is 12x squared minus 5y squared. Same also like f sub y. When we differentiate first term, we will get 0 because we will treat x as a constant. And for the 5xy squared, we will differentiate y only, and we will treat x as a constant, and we will get 5x in the bracket of 2y. And for the third term, we differentiate and we get a y cubed. So the answer is negative 10xy plus 8y cubed.
So for now, I will move to the rule for finding partial derivatives. So the first one is to find f sub x, we get y as a constant and differentiate f x y with respect to x. The second one is to find f sub y, we get x as a constant and differentiate f x y with respect to y. Okay, next we move to the example, which is if x y equal to x cubed plus x squared y cubed minus 2y squared. Find f sub x to 1 and f sub y to 1. So, for the step 1, we need to holding 1 as a constant and differentiating with respect to x. So, after differentiate, we will get 3x squared and 2xy cubed. Okay, then we need to substitute the value, which is x equal to 2 and y equal to 1. We will get 3.2 squared plus 2.2.1 cubed. We will get 60. Then for step 2, we need to hold in x as a constant and differentiate with respect to y. Then we will get 3x squared y squared minus 4y. Then we substitute the value again for f sub y, which is the value for x is 2 and the value for y is 1. Then we will get 3.2 squared dot 1 squared minus 4.1 equal to 8. So now we already find this f sub x to 1 and f sub y to 1, which is f sub x to 1 we get 60 and f sub y we get 8. Next, I'd like to discuss about function of more than two variables. A function does not have to contain only two variables like x and y. It also contains three or more variables. So, if you can see here, this is an example of a function with three variables, which is here you can see x, y, and z. X, y, and z are variables. The value of function x, y, z changes whenever one of these variables changes. So, this function also depends on all three variables together. Other variables are treated as constant during differentiation. Okay, we move to the example 1. Find sub x and f sub y if function x, y, z equal to x squared y, z plus 3x squared. So for the step 1, we need to find f sub x. So we need to differentiate only x. So we need to remember that if we differentiate only x, we need to treat y and z as a constant. So we differentiate the first term, partial over partial x times x squared yz equal to 2xyz. And the second term, partial over partial x times 3xz squared equal to 3z squared. So we get the answer, partial f over partial x equal to 2xyz plus 3z squared. So for the step 2, we need to find f sub y. So we need to differentiate only y. And we need to treat x and z as the constants. So we differentiate the first term, partial over partial y times x squared yz equal to x squared z. And the second term, partial over partial y times 3xz squared equal to 0. Then the answer for this, for f sub y, we get partial f over partial y equal to x squared z.
Now, let's look at this slide, which is interpretation of the partial derivative. First, what is z equal to f x y? It represents a trading surface as in the graph, which is this. First, partial derivative with respect to x. How to find is we fit y equal to b and hold y as a constant. This creates a curve cy. Therefore, f sub x AB is the slope of the tangent line T1 to the curve. Now, for the partial derivative with respect to y, how to find is we place x equal to a and hold x as a constant. This creates a curve C. So, f sub y AB is the slope of the tangent line T2 to this curve. Hence, this is line of T1, this is line of the T2, and this is curve of C1. So, geometric interpretation means that slope of a tangent line on a 3D surface. Now, let's jump to this example. This question asks us if f x y equal to sine x over 1 plus y. Currently, partial f over partial x and partial f over partial y. To solve this question, using the chain rule for the function of the one variable. Okay. Now, for the partial f over partial x. First, we differentiate sine, we will get cos. And differentiating the bracket, we will get 1 over 1 plus y. Differentiate x, we will get 1 and y stay as constant. Now for the partial f over partial y, first we will reach sign, we will get cos, and in the bracket, s over 1 plus y, but this formula is 1 plus y equal below fraction. So when you below fraction, we need to put negative. So it will be negative cos, and at this will be 1 plus y in the bracket of square.
Anyway, let's shift to higher derivative. Higher derivative, also known as second partial derivative, and obtained by differentiating partial derivative again. And it also functions of two variables. For the first line, you can see that this formula f sub x, which means we need to differentiate the function with respect to x, and then we differentiate again with respect to x. And the second one is we need to differentiate with respect to x, and then differentiate again with respect to y. And the third one, we need to differentiate with respect to y, and then differentiate again with respect to x. And the last one, we need to differentiate with respect to y, and then differentiate again with respect to y. Okay, let's move to the example. Find the second partial derivative of function xy equal to x cubed plus x squared y cubed. So the first step, we need to find f sub x, and you will get 3x squared plus 2xy cubed. And then we need to differentiate again the f sub x with respect to x. So you will get 6x plus 2y cubed. And then you need to differentiate again f sub x with respect to y. And you will get 6xy squared. Okay, the second step, you need to find f sub y, and you will get 3x squared y squared minus 4y. And for the f sub y, you need to differentiate with respect to x, and you will get 6xy squared. And then you need to differentiate again the f sub y with respect to y, and you will get 6xy squared minus 4. Last but not least, I will explain about Clauser's theorem. Clauser's theorem says that if the mid-second derivative f sub xy and f sub ys are continuous, then they are equal. F sub xyab equal to f sub yxab. That's mean the order of differentiation does not change the final result. Next, this concept can also be extended to third order or higher. We can differentiate even further to the third order, fourth order, or more. As example, for third order, f sub xyy, we can differentiate with respect to x first, then y, and then y again. Using Clauser's theorem, means third order derivative can also be equal. F sub xy1 equal to f sub yxy equal to f sub yyx. Let's move to the example. Calculate f sub xyz if functions xyz equal to sine in bracket 2x plus 4y plus z. The first step is you need to find f sub x, and then you will get 2 cos in bracket 2x plus 4y plus z. And the second step is you need to differentiate the f sub x, and you will get minus 4 sine in bracket 2x plus 4y plus z. And the third step, you need to differentiate f sub x with respect to y, and then you will get minus 16 cos in bracket 2x plus 4y plus z. And the last step is you need to differentiate f sub xy with respect to z. And the final answer is 16 sine in bracket 2x plus 4y plus z.
In conclusion, we already know the core rule, which is differentiate one variable at a time and keep the other constant. Second, We can visualize that we are just pointing the slope of a tangent line on a 3D surface. Last, we also learned that the attitude matter because f sub xy is always equal to f sub yx. That's all from our group. Thank you.